Good morning, everyone. Welcome to the Evan R. Liblit Memorial Scholarship Committee's sixth Waste on Wednesday seminar. My name is Mike Cahill, and I'm pleased to be your moderator today. I'd like to give you a little background on our symposium and our organization. For those of you who were not fortunate enough to know him, Evan Liblit was a very highly respected colleague who had worked with us and passed away at age 47 in 1995. And Evan's a way too short life. He worked for the EPA, the DEC, the town of Babylon, and in the private sector. He also found time to teach at our parent institution, Stony Brook University. In the mid-70s, while working for EPA, he organized one of the first office paper recycling programs anywhere. While working for the EPA, he was loaned out to the DEC. And in the 1980s, late 80s, he crafted the state's first solid waste recycling and solid waste management plan. He left the DEC and moved to the town of Babylon, where all of us on Long Island got to know him. And he pioneered what was then a very rare cooperation between the municipalities on Long Island and the formation of what became the Association of Long Island Recycling Officials. His energy and his personality motivated a lot of us while he was here. And after his passing, a number of his colleagues created the Evan Liblit Scholarship Fund at Stony Brook to continue his legacy. Over the last 22 years, our committee has been honored to have been able to provide scholarships to 21 graduate students and 16 undergraduates. Many have gone on to become leaders in their fields. Our funds are raised, or had been raised, at an annual breakfast that we held in November. But of course, this year, with COVID, we are shifting over to a virtual series of presentations. And ironically, with the advent of the virtual technology, we're more active than we've ever been. Last year, we had our first symposium at Stony Brook on the recycling crisis. And we attracted a standing room only crowd, and we thought it'd be good to go back and try to redo it. We had a symposium scheduled for March, but it was canceled. And these Zoom sessions are the follow-up. And this is our sixth. We expect we will have a seventh, and we hope to have an eighth. And if interest continues, we will continue to add topics. Sponsorships and suggestions for topics are always welcome. In terms of our logistics today, we will mute everyone except for the speakers. If you have a question for any of the speakers or just a general question at all, just put it in the chat box, and I will sort through them and try to make sure we get the essence of the question answered, especially if we've got the same question from more than one person. We may call on you, but our speakers will be available to answer questions at the end of the program. Today's topic is very important. It's waste to energy. And we have three very distinguished speakers that will address the state of waste to energy, both now and the potential for the future. Two of our speakers are from Covanta Energy. And one, of course, many of you know, is Derek Veenhoff. Derek is the Executive Vice President for Asset Management of Covanta, and he leads the company's $1.9 billion energy from waste business. He has broad oversight for the public sector service agreements for waste procurement and energy contractor within Covanta's infrastructure. Derek is also a board member of Covanta's United Kingdom-based energy from waste infrastructure, a JV partnership with Maccabee's Green Investment Group. Derek joined Covanta in 1996. He's a graduate of the University of Guelph in Ontario, Canada, where he was a published lead author and co-author of several peer-reviewed research papers on the topics of land use, environmental impacts, and waste management. Our other speaker from Covanta is Michael Van Brunt. Michael is currently the Senior Director of Sustainability at Covanta, where his primary focus is on sustainability strategy, planning, and reporting. His responsibilities also include climate policy and analysis, carbon offset project development, and life cycle assessment. Michael Van Brunt is a licensed professional engineer with over 20 years of experience in industry and consulting. He earned a BS and a master's in agricultural and biological engineering from Cornell. Our third speaker is another individual that many of you know very well, Bruce Howey. Bruce is a vice president and professional associate for HDR Inc. and currently serves as HDR's practice leader for energy from waste services. He has specific experience with the process, design, operations, and testing of various solid waste processing facilities, including waste energy and other thermal waste processing, such as gasification and waste to fuel technologies. Bruce has worked with the waste energy industry, of course, across North America for over 20 years. Recently, he's worked in the development of this industry in Australia and the Middle East. Bruce worked as a technical advisor for HDR on the expansion of the Lee County and Honolulu waste energy facilities in the U.S. He was the project technical manager on behalf of the regional municipalities of Durham and York in Ontario, Canada, during the planning, procurement, and construction startup of the Durham-York Energy Center, the first greenfield WE plant in North America in over 20 years. Mr. Howey received his bachelor's degree in chemical engineering from Manhattan College. He's a Jasper, and a Master of Science in Chemical Engineering from Penn State. Bruce is also a registered professional engineer in New York. I think we're going to have a very, very interesting series of presentations here. I will introduce first Michael Van Brunt from Covanta, and Derek will follow. And after Derek is through, we'll turn it over to Bruce. And when both presentations are through, we'll field questions and let our panelists do their best to answer them. Michael, it's all yours.
Great, thank you, Mike. Just to confirm, is that slide showing up for everybody?
Yes, it is.
Okay, great. Thanks very much, everyone, for being on the call this morning. I'll kind of get right into it. There's a lot of different ways of thinking about our industry and thinking about what we do. One of the ways that I like to think about it is thinking about our industry as sort of dealing with and minimizing the environmental impacts of the wastes that our society makes. We're in a position of sort of, taking the waste that society makes and figuring out how do we manage it in a way that has the least environmental impact. And hopefully a lot of you have seen this before. I mean, certainly a lot of people are very familiar with the mantra, reduce, reuse, recycle. There's actually a more complete hierarchy that sort of orders all of the major technologies and the descending preference of environmental impact. A couple things that I think are important to note is that this hierarchy sees parallels both in the EU and US EPA. And the thing I really like about the way that the Europeans structure their hierarchy is that they draw a very distinct line between waste prevention and all of the other management approaches. And I think that serves as a really important reminder that everything that we do, once you put waste out onto the curb, has some form of an environmental impact. And certainly a lot of the discussion that we've had recently that we've all dealt with regard to the pushback from China in terms of contamination, and most recently with the Climate Leadership and Community Protection Act in New York, we're all sort of looking again at sort of the waste management approaches from that environmental framework. And I think very appropriately taking a more expansive view of it. And where energy from waste fits in, or waste energy, really fits in as sort of the preferable option after what's left over after recycling efforts have been exhausted. And years ago, I think this really started around the idea of materials efficiency, energy recovery, sustainable use of land, and over the decades, particularly as climate has become a greater concern, we found that the climate change impacts are roughly in order with this hierarchy as well. And so if we look at those two choices left over after recycling, landfilling and waste to energy, it's still the two predominant ways of managing waste that's left over after recycling. We can get into a little bit of the detail in terms of what drives that ordering in the hierarchy. From the climate perspective, landfills are a major source of man-made methane. Globally and in the US, landfills represent the third largest source of methane. And methane is interesting greenhouse gas because it is very, very potent, yet has a relatively short time frame in the atmosphere. So when you look at methane's impact over a 20-year perspective, as we're starting to see more policymakers and scientists do, methane is actually 84 to 86 times stronger than CO2 in terms of its impact on the climate. Turning to other non-greenhouse gas issues, and certainly one that's of particular interest, I think, to folks in California, is the risks around leachate generation and groundwater contamination. A lot of times you'll hear people within state regulators and the EPA talk about, it's not if landfills are going to leak into the environment, it's when and what's the impact to the surrounding community. Land use, another issue for folks on Long Island. It can be a very difficult and sort of non-sustainable use of land. And the energy recovery we get out of landfills is important. Certainly, if we do have landfills, we like to see energy recovery systems put in place. But relative to what we're able to capture from a waste energy facility, it's a relatively small amount of energy that you can pull out of that waste resource. Looking at waste energy, many of you sort of familiar with this, we get a very sizable size reduction in the amount of waste that's generated, about 90% reduction in the volume. And increasingly, looking at sort of metal recovery. And Covanta and the metals management team of Covanta have spent a lot of time and invested a lot of effort in recovering and improving our metal recovery over time. And it's something that continues to be an important focus. And I know Derek will speak about that a little bit more during his presentation or his piece of the presentation. And if we look at things from a climate perspective, turning to that back again, every ton of waste nationally that we're able to divert from a landfill to a waste energy facility saves about a ton of greenhouse gas emissions as CO2 equivalents. And that's a fundamental benefit of waste energy over landfilling. And it's one that we often get a lot of questions about because it's not necessarily intuitive to tell somebody that a facility with a stack has a greenhouse gas benefit. And the reality and sort of what drives that really has to do with what would have happened if the waste did not wind up in a waste energy facility. So if we look at this chart, the first bar all the way to the left-hand side shows the picture if we look just at the stack in terms of what the CO2 emissions are. And we find that roughly for every ton of waste that we process, we emit about a ton of CO2. 2/3 of that CO2 in terms of what we monitor today is from biogenic sources of waste. So think about food waste that's not sent to an AD facility, or the paper, cardboard that hasn't been recycled. That all contributes to that 2/3%. The remaining 1/3 of the waste that we process and the carbon in the waste that we process is from plastic materials. So think about non-recyclable plastics, plastic films, containers that don't get recycled. And that's typically what the focus is on a public policy perspective, is reducing those fossil CO2 emissions down to what we possibly can. And so that's sort of the basis for the comparisons on a life cycle basis that the US EPA and others do. The second bar then starts to look at what would have happened if the waste energy facility were not in place. And the first piece is what we would have needed to make that electricity from another resource. And still today in New York and in other places, we still generate a lot of our electricity from fossil fuel fired power. So that is a significant benefit that our facilities are able to deliver. We recover about and put out onto the grid about 550 kilowatt hours per ton of electricity onto the grid. And then we also have some facilities. We operate a facility in upstate New York in Niagara Falls that supplies a significant amount of steam to a local industrial loop. And so again, that was very effective in terms of, in that location, actually displacing old coal-fired boilers that individual manufacturers had in place that were replaced by the steam loop that we feed into. The third benefit that we're bringing is we're pulling out metals for recycling. And metal production from raw materials is a very energy and greenhouse gas intensive process. So anything that we can pull out of the waste stream, whether it be on the front end or the back end, has a significant greenhouse gas and energy benefit. But by far the biggest benefit that a waste energy facility brings from a greenhouse gas perspective is the ability to completely avoid all of the methane that would have been generated from that waste had it been placed into a landfill. And in this particular assessment, we did this specifically looking at the way that New York has chosen to look at its greenhouse gas impacts under the Climate Leadership and Community Protection Act, and looking at that methane 20-year greenhouse gas impact, but conservatively only assessing the first 20 years worth of landfill methane. There's a lot of discussion in the scientific community what really is the appropriate way of doing that assessment, but this particular perspective is very conservative as it only takes into account those first 20 years. So you sum all of that together, taking into account our positive greenhouse gas emission at the stack, but also considering the benefits that the technology brings. And in New York, under the Climate Leadership Act, we actually are reducing emissions relative to landfill by about 1.3 tons of CO2 equivalents per ton of MSW. And importantly, it's not just us saying this. It's very widely accepted internationally in terms of the benefits that waste energy brings, anywhere from the European Environmental Agency to the IPCC, which called waste energy a key greenhouse gas mitigation technology, to the UN and the Rio UN conference, World Economic Forum. The original Clean Power Plan as proposed by the Obama administration would have considered waste energy to be an option for reducing a state's greenhouse gas emissions. And we actually have 3 facilities that have been approved to generate carbon offset credits, and 2 of them sell those credits into voluntary carbon market. And if we look back at New York, one of the challenges that the state faces is how to deal with the emissions from landfill methane. And amazingly, landfill methane is 11% of the state's greenhouse gas baseline, which is just an amazing amount for a sector that typically doesn't get a lot of attention when it comes to greenhouse gas policy. And when we look at it, it's even more than residential fuel combustion. And the challenge that the state is going to face is that we really don't have great end-of-pipe options for controlling the methane that landfills emit, which goes back to the waste hierarchy. The best form of environmental protection often is prevention. So the more waste that we can divert out of landfills, the better chance we stand in meeting the state's targets. And part of the challenge is that we're finding is that when we actually get out and measure methane emitted from landfills, it's coming into about double of what the predictions initially thought. And when we turn even to like sort of California has struggled with this for the last almost a decade now, and implemented as part of their greenhouse gas reduction program what they call a series of early action measures, and implemented the most stringent landfill gas control regulations in the country. And even with those regulations, when NASA did a study of what the methane emissions were and what the methane sources were in the state of California, they found that landfills were the largest point sources of methane in the state, and characterized those a subset of landfills as being methane super emitters. And that really underscores the challenge that we face with regard to trying to control methane after we've put the waste in the landfill. It's just extraordinarily difficult to capture what we need to do to reduce greenhouse gas emissions. And so what that really brings to us is what really are our options. It's pretty clear that the Climate Leadership and Community Protection Act, it's going to impact every single sector in the state's economy very significantly. Getting the economy of the state down to net zero carbon by 2050 is just a phenomenal task. And it's clear in the waste sector that we just really need to get out of the business of landfilling. We need to find better things to do with the waste, whether it be recycling, composting, anaerobic digestion, but also using waste energy sort of as appropriate to help us reduce emissions from the residues that are left over after recycling and composting is exhausted. And I think there's a few things here that we just wanted to point out. In order to get down to that net zero greenhouse gas emissions, even the waste energy sector is going to have to take a hard look in terms of what our facilities look like in, say, 2040 and 2050. And what I like to think about our facilities is sort of really important technology platforms that we can do a lot of, carefully engineered solutions and bring those to the table. Recognizing that there's always going to be a residual waste that we need to manage, and that residual waste is going to have some form of an impact. And waste energy facilities give us an engineered potential to actually reduce and minimize that impact. And one of the really great aces in the hole that I think we've got as an industry is that one of the things that the IPCC has pointed out is that in order for the world to get to a net zero greenhouse gas scenario by 2050, we're going to need to figure out how to do some carbon removals from the environment. And one of the best ways of doing that that's available to us today is figuring out how do we capture biogenic carbon. Biogenic carbon, that's the carbon that's part of that normal carbon cycle. And so if you're actually able to pull biogenic carbon out of the flue gas stream and sequester it or use it, you can then take that facility and make it into a real greenhouse gas negative solution that can help offset some of the emissions that might occur from other sectors of the economy that cannot be decarbonized. And the beauty of sort of the waste sector is that the biomass that's there is not at that point contributing to land use change. So one of the concerns a lot of people have about bioenergy facilities or purposefully grown biomass is that you have to really be very wary about what impact is that having on land use change, and what are the emissions associated potentially with converting forest land to a grassland. Waste sources of biomass, give us an opportunity that we don't necessarily have in other sectors. So that sort of summarizes a little bit in terms of where we see the role of waste energy under the Greenhouse Gas Reductions and the Climate Leadership Program. I'm going to turn it over to Derek to talk a little bit more in concrete terms of how that might play out from a business perspective.
All right, thanks, Mike. And good morning, everyone. It's a pleasure for me to be here and take part in this. So when I look at this slide, and I think about some 32 years of passing, I think back to the town councils and the town supervisors in the early 80s, mid 80s, making some really, I think, probably contentious decisions. I was just a high school guy back in the early 80s, and then off to college in the mid 80s. And I think back to those days. There's some phenomenal infrastructure that was built, and the decisions that were made at the time to do that, I'm sure, were not easy. And, there's some approximate numbers on this page, on the slide, that kind of give you a visual or a mental view of what those decisions really added up to. Forgetting about the economics for a second, just in terms of managing household waste over the period of time and doing it, very, very safely, I might add. So sustainable waste management, almost 50 million tons of waste since 1988 has gone through the 4 energy from waste plants on Long Island. That's saved basically 389 acres that would otherwise have been devoted to landfilling, the MSW equivalent. On the energy side, basically 25 million megawatt hours generated, which translates to 77,000 homes powered for every year. So if you do the math on that, usually I leave math for Mike because he's a really good brain, but I did the math. It says 2.3 million homes for a year powered. So not an insignificant amount of energy created from the energy from waste process over the time frame. And they're really cool for those of you who've been to California and have seen the Golden Gate Bridge. Imagine 13 Golden Gate bridges that were made out of reclaimed metals out of energy from waste, which is what the amount of metals that are coming off the 4 energy from waste plants that are out on Long Island. So pretty significant. And when you think about the avoidance of the extraction of the raw ore, you know, I think that there's a multiplier effect even around that recycling initiative. And these are metals that are otherwise aren't really effectively captured for the most part by household recycling or commercial recycling programs. And then Mike's already talked about the greenhouse gas significance. You know, Long Island's all about transportation and how quickly you can get from A to B. 9.6 million cars taken off the road from an equivalent standpoint, 50 million metric tons of carbon dioxide equivalents. So that's I think that's quite a track record for the plants that are on Long Island. So Mike, if we can go to the next slide. So when I look at this slide, I think about, well, what's really the opportunity? So you have the 4 energy from waste plants on Long Island, and you can see they tend to be focused, I would say, on the western end of the island. We have 4. Covanta currently owns 3 and operates 1 for a client, where all 4 of those plants are technically expandable. So what does that really mean? Well, we know that there's over 1 million tons a year of municipal solid waste that's leaving Long Island, and it's leaving Long Island by truck. So when you think about that, and you think about making fundamental improvements around infrastructure and on ways of life, I would argue, if you're stuck in traffic, frustrated with how long you're stuck, anything that we can do to clear the transportation lanes of unnecessary truck traffic, I think is fundamentally very important. Takes a lot of risk off the road, and it also has an environmental impact at the same time. So these 4 waste energy plants, it's about 1.8 million tons per year that they're consuming of household or commercial solid waste. They're generating 125 megawatt per hour of installed capacity. So we're putting renewable energy out onto the grid. And interestingly, University of Buffalo did a study on our Niagara plant in Western New York, which was an economic evaluation of the impact of the facility. And the University of Buffalo spent, I think it was well over a year doing research, and they came up with a figure. It's really, you know, quite astounding. They came up with an economic multiplier impact of basically $162 a ton. So if we take that number and we apply it to Long Island, to what's our 1.8 million tons a year, you end up with $290 million of economic output. So also not insignificant. So Mike, why don't we go to the last slide? So part of my job is a little bit of a salesy job. Mike's the science guy. My job is a little bit of the sales guy. So I like to think about, well, really what's possible for energy from waste on a go-forward basis. And I like to think about this in the context of, you know, when I mentioned in the mid-'80s, I think back to the telephone, and, you know, nobody had a cell phone really, unless you were in the military. And, you know, if you were traveling somewhere and you needed a phone, you were in a phone booth, adding quarters, trying to make a call, trying to figure out where you needed to get to, right? And today we have a smartphone at the tip of our finger that gives us more information than we possibly know what to do with. But at the same time, when you look at energy from waste, the basic fundamentals of energy from waste are still as strong as they were in the late 80s. You know, good mass burn technology coupled with sophisticated air pollution control has done remarkable things. It's after 30 years, it's still performing well, and we've been able to drive emissions even lower over that time frame. So we know that this technology works. We know it's reliable. We know it has benefits, right? So we can continue on Long Island, where there's more waste available. We know we can generate more energy from that waste. Now, energy as we move forward might come in a different format than a little bit of what we're used to, right? So we have a lot of renewables on the grid today. Wind, solar is coming. But we also know that the transportation network is changing. And nowhere is that more evident than in California, which I think just the other week passed a law essentially saying the internal combustion engine was not to be on the road in 2035, which is a very, very lofty goal. So we know that the transportation sector in particular is moving to a different format of fuel. That could be electricity in the form of cars. It also could be hydrogen in the form of heavy vehicles. And there are parts of the world in Japan and Germany that are very much focused on that and bringing that to reality. So I think when you think about energy from waste as we move forward, I think you need to think of it as something that has multi-fuel capability that society's going to need. On the metal side, we know that, and we've spent the last 10 years focused on technology, on metal recovery. And we know that business of metal recovery has rapidly changed over that last 10 years. So we know that there's more metals in the ash than prior technology was able to extract. And of those metals, there are metals of particular value. And those are the non-ferrous metals. And on a go-forward basis, I think it's safe to say, particularly as it relates to non-ferrous, it's quite easy to think of non-ferrous as being double the amount that we've been reclaiming, if not higher. So, and that's material that's readily recyclable, high-value material that we haven't been able to capture until recent years. Which brings me to the ash recycling standpoint. Over the last 10 years, we have been doing a lot of R&D, and a lot of it was focused around the municipal solid waste ash that we generate from all of our plants. And for those of us who have been in the business a long time, we've always looked at ash saying, how do I, when you're around it every day, you realize that there are pieces of that ash that have value, but we're paying to get rid of it. And so right now we're in the commercialization phase where we have an ash processing system that we've built in Fairless, Pennsylvania, that's designed to handle 400,000 tons a year of ash coming from a number of our Covanta plants in a regional processing plant. But the goal is to extract the valuable metals to the very, very small sizes, so that ultimately you end up with an ash stream that doesn't contain metals. And you have an ash stream that then you can put to work as an aggregate, or at least components of it. And so we've explored this. We're pretty far along. And we think ultimately that, the number that I have on the slide says 30% of the residue, ash residue materials after this total ash processing component would end up going to landfill. It could end up being less than that. And we're finding some of these materials are quite desirable materials, and they might be superior materials relative to the materials that people are currently using today. So I think this area has a very, very bright future. And it's being accelerated, of course, by technology, just as everything around us is moving forward. So the plan of the future, and this is where we're going to lead into Bruce. I think Bruce probably has some really great insights around this. But the plan of the future, our experience at Covanta, we have some recent construction activity. The plant that you see here is in the Port of Dublin. That's a 600,000 ton a year plant. Aesthetically, if you're in Dublin, you would be saying, wow, this is a beautiful, I think it's a beautiful plant. I tell people this all the time. It's aesthetically quite pleasing, but very sophisticated on the inside. You know, lots of room for workers, a really nice work environment for folks, and extremely low emissions. So we know that, and we're currently building 3 plants in the UK. They're in construction right now. We hope to have a 4th come early next year. But we know these plants are highly sophisticated. They are state of the art, and they represent the future of building energy from waste plants. And I think it's a very exciting time. You know, we can call this generation 1, the last 30 years. Generation 2, I think we'll look back 30 years from now saying, wow, those were some great decisions that were made around these plants. So with that, I'd like to turn it over to Bruce.
All right. Thank you, Michael and Derek. Get my PowerPoint presentation up here. Everybody can see it okay?
Yep.
Okay, great. All right. So number one, thank you, Michael and Derek, and also thanks to Mike Cahill and Caitlin and his team for inviting me to this morning. So it's my pleasure to kind of give everybody a little update on sort of where waste energy technology is, both from a sort of global perspective as well as some of the projects that are going on in our backyard right now in the U.S. and across North America. So it's just a little overview of the presentation today. I'd like to kind of start off by talking a little bit about sort of where we started and kind of where we are now. And so as a sort of way of history, you know, in the 50s and 60s is really when Europe started to build their first sort of modern, what we would call modern waste to energy facilities using combustion stoker technology and recovering the energy to create steam and electricity. And U.S. took a little longer to catch on to that. In the 70s, as many of you know, the majority of our facilities were built in the late 70s and early 80s, and a lot of those facilities are still in operation today, including the 4 that are out on the island that Derek mentioned. The 90s, particularly the late 90s, which is when I got my start in the industry, was really more focused on the Clean Air Act amendments and retrofitting a lot of the facilities that were built, particularly the facilities built in the late 70s and early 80s that weren't built with the Clean Air Act amendments in mind. And that's kind of how I got my start in the industry, working on those retrofits, including at the Iceland MacArthur facility. And then in the early 2000s, we started to look at expansion of some of the existing facilities. You see the Lee County facility there, which is a Covanta-operated, county-owned facility in Florida. There was also the Hillsborough County expansion, Hawaii expansion, and a number of other expansions that occurred during the sort of early mid-2000s, you know, to expand existing capacity. You know, after the sort of great economic downturn, you know, in the early mid-2000s, there was a lot of discussion and interest in building new facilities, which we hadn't talked about in a long time. And a combination of the, you know, sort of economic downturn as well as energy pricing just kind of going into the floor with discovery of shale gas and sort of HDR, sorry. The United States, there's my commercial, so I apologize. But the United States becoming really an energy exporter, the price of electricity really drove down the economics of a lot of those projects, and really only 2 in North America got out of the starting gate and implemented. But that being said, in the present day, there's still a lot of activity in Europe, as Derek mentioned, and in Asia, and there's still interest here in North America as well. And there's a lot of discussions about expansions, particularly in certain geographies of the U.S. and even some contemplation of new capacity in parts of Canada and other parts of the U.S. So just really quick on what are some of the drivers and challenges to new development and technology development. And some of the drivers, as Mike and Derek already mentioned, it's recycling and the need to increase recycling and the desire to do that and the increasing landfill diversion goals, and trying to sort of pivot to look at recovery as part of the waste hierarchy and not just the 3 R's and then with disposal. And all of those are things that the EPA and other organizations recognize, as Derek had mentioned, but it's still a challenge to sort of get over that hump. Another driver really is the China National Sword Policy. A lot of the non-recycled plastics that we used to send over to Asia if they're not being sent back, we can no longer send them there. And there's a lot of renewed interest in how do we manage that waste stream and what technologies are out there to help manage those waste streams, whether it's traditional or alternative technologies. PFAS, or per and polyfluoroalkyl compounds, and I'm stretching my chemical engineering background to even pronounce it, but that's really become a hot button issue over the last year. These are compounds that can be found in anything from stain and water resistant carpeting or clothing. It's very common in fire retardant, so it's very concentrated around military bases sometimes and airports. And there's a growing concern, whether scientifically justified or not, that those compounds are in the waste stream and in the environment. And thermal destruction of those compounds are really one of the few sort of methods of disposal that have been recognized so far by EPA. But there's a lot of science that still needs to be developed and understood about those. But it certainly has become part of the discussion in our waste to energy facilities, or even biosolids incinerators that are still in operation. Is that a potential source for treatment and destruction of PFAS? And then, of course, and I think Michael summarized this quite well, renewable energy and greenhouse gas mandates and how waste to energy is considered really helps reduce those impacts versus other methods of disposal or treatment. The challenges are challenges that we've been talking about for, at least the 20 years or so I've been in the industry, and many of you have been in the industry beyond that. But the challenges are always, we still have a lot of landfill space and it's cheap. And we may not, although it's an issue, particularly out on the island with, the decrease in capacity and the inability to build new capacity. In other parts of the country, it's not so much an issue, and it's still very much a cheap source of disposal and highly used, particularly in the Southeast and the Midwest. Energy is still relatively cheap in this part of the world compared to other places, and I'll talk a little bit about the difference between the challenges and drivers in Europe and Asia versus here. And then opposition to these facilities, even gasification, is still very strong. You look at a place like California that Derek mentioned, as out in front they try to be with their diversion goals and recycling goals. They really never have met any of their mandates for 70% diversion by 2020, or some of the more aggressive ones that are 5 years off. And part of that is because of the sort of narrow view of what thermal treatment is, both from a gasification standpoint and from a traditional waste to energy standpoint, and how that sort of fits into the hierarchy and recycling industry. And then there's really no cohesive regulatory framework like that you might see in other parts of the world, like Europe. And, good luck getting the federal government to agree on anything. We came close with some of the Obama's legislation, but it's really the leadership's going to have to come from local municipalities and local areas on sort of moving some of these projects forward. So just a really quick sort of technology 101, and I won't get too far into the theory here, and really my focus today is more on thermal treatment or thermal technologies like traditional mass burn or RDF combustion technologies, which use, excess air or a lot of air to treat and combust the waste. And then we'll also talk a bit about gasification and pyrolysis and plasma arc technologies, which typically operate under a substoichiometric or less than excess air, or in the presence of very little air or oxygen or no oxygen at all. But there are other technologies out there, obviously biological treatment, and there's a lot of interest in anaerobic digestion for treatment of organic materials, which is really, a proven technology for something like sludge or biosolids, but it's still in development, particularly for a mixed municipal waste stream. But it's a growing interest, particularly in parts of up north, the north of the border in Canada, and out west in California, and in parts of the Northeast as well. And then we'll talk a little bit about, sort of mixed waste processing technologies, but I combine those really with a lot of these alternative thermal treatment technologies, which require some front-end processing, or they're part of a hybrid type system that may use a front-end, a very elaborate front-end system to separate out the different materials, followed by a thermal treatment process, and then sometimes a chemical treatment process to create a fuel. I always like to, when I speak to groups like yourself or municipalities or industry groups, I always like to try to classify waste conversion technologies into two pieces. There's the established technologies like mass burn or RDF combustion, and I think Derek made this point previously. I think the stress that the facilities that are being built now are not your grandma's waste to energy plants. They're far more efficient from an energy production standpoint, as well as from a flue gas and treatment and air pollution control standpoint than the facilities we built even 30 years ago or 20 years ago. So the technology, whereas we kind of stopped building them here in the U.S. for a number of reasons, in Europe and in Asia, they never stopped really. And instead of halting the industry, they really developed them and sort of fine-tuned them to be really efficient and clean facilities. And then there's emerging technologies, and some of these technologies may not be considered emerging in other parts of the world, but I'll talk a little bit about the differences there. But those emerging technologies are really that they haven't had a wide commercial application like gasification, at least for mixed municipal waste, or pyrolysis or anaerobic digestion, that at least here in North America and in the US, it's still in various phases of development and starts and stops and successes and failures. So this is just a sort of quick overview of advantages and disadvantages, and I'll make the presentation available to folks, but I'm going to keep moving if that's all right. So just to kind of go through a little bit of a global perspective on the view of waste to energy and where the technology is abroad, and Derek touched on this particularly in the projects in the UK and in Ireland, but the EU has a landfill directory, that requires some pre-processing before you can put it in a landfill. If in some countries you're allowed the landfill at all, like countries in Denmark or Germany, there are landfill bans, and in most EU countries, if there's not a ban, there is certainly a financial disincentive to put it in a landfill, either taxes or levies, like in the UK, for example, that make it incredibly expensive, sometimes $100 a ton on top of a gate fee, that make it very expensive to put it in the landfill. And again, they have different drivers in the EU. They don't have the space that we have here, and that drives a lot of it. But it's also an environmental sort of responsibility that they feel that it's. I've heard Europeans, when I've been over there, call it interim storage, that at some point or other, it's those liners are going to fail, and it's just a more responsible method to treat it in some manner before it gets put into the ground. They also have higher energy pricing, and there's government incentives that exist in the EU and in some of the EU member states or in the UK whether it's on the power they buy or on the projects themselves, that just don't exist here or in other parts of the world for that matter. Most of the technology used EU-wide is, mass burn technology or stoker grate type technology. There's some RDF combustion. They've dabbled in gasification, and there's certainly some countries that still, I think Germany has tried it. They don't really, I think from an economic standpoint and a technology standpoint, they favor mass burn technology, as do most of the northern and Western European countries. But there is still some development, particularly on specific waste streams, whether it be plastics or hazardous wastes, that they'll use the high temperature type gasification projects to treat those wastes. But overall, when it's municipal solid waste, it's typically a thermal combustion type stoker project. And, that being said, they still have very strict environmental regulations in the EU, and emissions requirements, much more stringent than the US in most cases, and they're able to meet those with mass burn technology. And it's widely accepted. And this is a good example, and I think Derek was alluding to this in his presentation, that, they also take a very different approach to how they build and, the aesthetics of these facilities. Very often these facilities sit right in the middle of a city. Copenhagen is a good example. There's 4 to 5 facilities in Greater Copenhagen that all feed into their district energy system. And this was one they constructed a couple of years ago that actually has a ski lift on it. So, money is no object apparently, but it is certainly something that they take a lot more pride in these facilities and take a lot more pride in developing the aesthetics. This is another project. This one is in the UK in Oxfordshire. And you can see, again, it's more of an example of just the types of how they expand the architecture and really, they want these facilities to be a showcase because, again, very often they're right in the middle or just outside of a town, and they provide district energy as well as electricity to that community. Europe, hasn't gone without its, challenges and failures. I'm sure many of you heard about the Tees Valley project, and this was a plasma arc facility or technology. Alter Energy was the main technology provider for this, and Air Products, which is a major gas provider company in the U.S., was really backing this project for a number of reasons. And it was, this is a good example of the dangers of scale up, and that, the technology that Alter Energy had been using, or at least had applied in parts of Asia, was maybe at most 200 to 250 ton per day sort of modules. And this was a scale up to 1,000 tons per day. So that, that 4 to 1 or 5 to 1 scale up, really was never proven. And they ran into a lot of design and operational difficulties, and ultimately financial difficulties getting that facility online. And eventually Air Products walked away from it, at a loss of almost $1 billion US. So, you will see some more of these as I go through the technologies. And I'm technology agnostic, but also as an engineer, and often advising communities like out in the island or wherever I've advised clients. I've got to take that level of caution that, things like scale up are important. Things like experience with similar feedstocks is very important. And this was sort of a good example of a lot of money being spent without sort of fully thinking through whether the project was going to be successful. Asia is interesting and very different. Certain parts of Asia are very similar to Europe, particularly Japan. They don't have a lot of space and to get rid of waste. They can't landfill, they don't have a lot of landfill space, or each prefect in Japan is required to manage their own waste streams. So a lot of their drivers are, very high population, not a lot of space to build additional landfill capacity, In places like China, it's kind of a shift to be more responsible and find ways of treating it versus landfilling it. And so they're open more to not just thermal traditional waste to energy. And Japan certainly has a lot of, traditional stoker type technologies implemented all over Japan, but they are also more open to gasification like technologies. And I'll talk about some more of that. And in Japan, they may have a stoker technology, and the ash residue that's coming out of the back end of that, traditional waste energy facility will then go through a gasification or ash melter process to vitrify the ash or further treat it so that they can use it for road base or to, as a fill material, which is, very different than how we treat ash here in the U.S., as Derek had mentioned. And China is really a booming market. I mean, I think at one point, obviously before COVID, I heard they were, putting in construction as many as 100 facilities, and obviously they can move things a little faster for, various reasons, but that's really a booming market as far as waste to energy. And then there's other parts of Southeast Asia as well, like Vietnam and other countries that are looking at it seriously or have built facilities. So this is an example of a gasification plant. And, I've had the opportunity through HDR and also work I've done for the Air Force to go to Japan and visit some of these facilities. And, it is a mixed waste material. Obviously, I think Japan is very regimented as far as what they separate. And if you go into a McDonald's in Japan, there must be 4 or 5 bins. And one of them even includes sort of a bin with a little fire on it to indicate that that's stuff that will go to the waste energy facility. So obviously they're very regimented in how they separate their materials at the source. But at the same time, they are, because of regulations and again, because of limited landfill space, they're also often more open to some of these gasification technologies. And this facility, as well as the next one I'll talk about, that I had the opportunity to go to, it's a mixed waste material. I mean, you can look in the pit and it looks like our garbage, although a little more separated. And they process it. I think the important thing to understand too is, when I've gone there, they don't necessarily try to reuse the syngas and create a fuel or something out of it, like some of the technologies that are advertising here in the U.S. or other parts of the world. They almost treat that gasification technology doesn't look much different than a mass burn stoker as far as having an air pollution control back end that, cleans up that syngas and then releases it through the stack, and they just recover the heat from that syngas in a heat recovery steam generator or boiler, similar to how we would in the 4 facilities out on the island. They're very weary, and they've tried to do more with that syngas, and I think they feel that the technology and the science just quite isn't there yet to make it economically feasible. So that's an important thing to understand when you hear some of these technologies come out and say, yeah, we're going to convert this into a fuel or some sort of biofuel. So I'm kind of coming back to the U.S., just by way of background a little bit on sort of where things are. We still have around over 70 facilities in operation today. That number seems sometimes to shrink every year, unfortunately, due to economic reasons and even, socioeconomic reasons, facilities being closed down or being forced to close down. But we still, landfill a lot of our waste stream and less than 10%. And like I said, that number probably continues to dwindle of our waste stream in the U.S. is actually processed through a waste to energy facility. There still is a lot of discussion of expansions or even, building new facilities, again, particularly in certain parts like Florida, or maybe, there's consideration on the island for that matter, given some of the challenges out in the island. But, the challenge still remains to be cheap landfill costs and sort of looking at the economics a little differently, where, we're not going to get the same electrical pricing that we got in the 80s or 70s during the oil energy crisis. So how do we, sort of pivot what we traditionally did with these facilities and maybe open them up to different sort of, other initiatives like Derek mentioned, the zero emissions initiatives and electrification initiatives that are being contemplated on, particularly on both coasts with converting fleets to electrical or that move to electric vehicles. So I know we're running up against time here, Mike. I'll go through this quick, but Mike mentioned, and as the Derek, the Durham York Energy Center up in Canada, I had an opportunity to work on this project along with Derek. And, you can see that at least up there, they kind of approached it from that European model, at least from an aesthetic standpoint. But even, inside the facility itself, it's a high efficiency boiler, produces, even for a relatively small facility, it produces a fair bit of electricity for its size. And the air pollution control on that facility is also state of the art because the municipalities, in order to get it moved forward, really went to the best of European standards and U.S. standards and Canadian standards to get that facility approved. And that facility came online in late 2015, and we've had its bumps and bruises, but it's operating quite well now and it's reliably and very cleanly. Many of you may have heard about the Enerchem project. You probably haven't heard a lot about it other than it exists, and you're not alone. I've been to the facility a few times. This is a good example of a sort of hybrid type system where it's a mixed waste front end process. Really, that was built by the city of Edmonton to separate out different materials and improve their recycling and also to capture organics. And the sort of off stream of that mixed waste processing or front end system is this sort of spec fuel, I'll call it, that goes to the Enerchem biofuels facility. And they take that fuel and convert it into methanol and then ethanol through a sort of a Fischer-Tropsch type process, gasification and then Fischer-Tropsch type process, which, is a proven process certainly in the petroleum or the oil industry, but not so much in chemicals industry, but really, not quite proven for a mixed municipal stream. They claim to be converting, the waste into 10 million gallons a year of ethanol, but depending on who you speak with, and it's very hard to get information from these guys. When I was there, to be honest, I wasn't sure if they turned it on, an hour before I showed up, but they are still out there trying to do it. And to their credit, unlike some technologies that have tried and failed in the UK or even here in North America, they have tried to do it from a scientific sort of stepwise process versus, all in going to a commercial scale. They started out on a pilot scale in Quebec, and then, they've ramped it up to this scale. And, we wish them well. The current state of the facility is a bit guarded. Fiberite, which is built a facility up in Hampton, Maine. Again, I tend to be technology agnostic, and I don't want to always seem like half empty. I'm an engineer, so I think it's twice as big as it needs to be, not half full or half empty. But I think in this case, this project was touted, and a lot of the local communities signed on to this technology. They were going to process up to 400 tons per day of MSW for those surrounding communities. And it's you could see from the picture, very high tech, very complex front end process. They were looking to target the organics stream and create a biogas from that using AD, as well as create a solid residual fuel or SRF that could be used with any other technologies like gasification, or it could have been used, say, by a cement kiln or some sort of local industry to displace the need for coal or fossil fuels. it had some delays in construction and startup from the start. It finally opened in 2019, but earlier this year, they announced that they were closing indefinitely due to financial and I think some technical issues. And the towns are currently looking for a new buyer and operator for that facility. And there's other projects out there too. Derek and Mike mentioned the interest in hydrogen and that sort of shift to a hydrogen economy. There is a fair bit of interest in waste to hydrogen. I've worked on projects in the Middle East that, of all places, where they're interested in looking at that. I don't think the technology is quite there yet. Japan has been playing around with it a bit. And this is a Japanese technology that they're trying to implement out in California for certain waste streams to develop hydrogen. And it's still very much in the planning and construction phases, and it's probably not expected to start up till later this year. And I think it's important to note too that most of the experience has been very much on a small scale, not large scale ton per day type projects that you'd see like maybe with a conventional waste to energy facility. Another growing sort of driver or interest in the thermal and waste conversion market is plastics to fuels. I mentioned the China sword issues with that and the non-recyclable, basically 3 through 7 plastics. There is, a fair bit of, I'm very hopeful or optimistic about these types of technologies for plastics because it's more of a homogeneous fuel stream, and there's some sort of history behind the ability to convert those streams into either a crude oil or some sort of syngas that might be used. And there's a number of technologies out there, both that are different scales of in the U.S. As well as, on a commercial scale in other parts of Europe or in Asia. So it's, again, still being developed, but it's got a lot of growing interest in different parts of the U.S. as people try to, or in North America in general, as they try to figure out what to do with those waste plastics that we can't really find a recycling home for. So I'll wind this up, just some final thoughts. And I think, the important thing to note that, this is still very much a challenging industry. I think there continues to be that need for education at all levels, whether all levels of government or regulatory agencies, and in the general public on what waste to energy is and how it's used around the world. And as well as on technologies. A lot of the times these technology providers, they don't come to guys like me or public works directors. They go to the politicians and say, we're going to turn your phone books into gold. And then it sends folks on a goose chase onto whether it's really real or not. But I think there's a place for alternative technologies as well as traditional waste to energy, and that fits in within the waste hierarchy. And I think with the alternative waste energy technologies, like gasification and pyrolysis, there needs to be a little more research and advancement in that technology and really sort of pinpointing what feedstocks it works best for and what the financial feasibility of those types of projects are, and take some of the lessons learned both from the Europe and Asia as well as here in North America. We've had our share of failures as well to sort of not make the same mistakes again. And again, this is in the current times we're in. That last bullet point, cooperation amongst all government levels is a big wish item, but that's really what's going to take to sort of get some of these projects across the finish line. So with that, I thank you, and I'll turn it back over to Mike.
Well, thank you, Bruce, and thank you, Michael and Derek. That was a lot of information, and I'm glad we got everything in. We're going to go a little over. I guess I'll remind everybody, if you have a question, just stick it in the chat box, and I'll pass it on to the panel. But also remember that this Zoom session has been recorded, and you can get it. And if you wanted to show it to somebody else, which I think a lot of you might think about doing, it's available from Stony Brook, and you can send an email to me or to Caitlin, and we'll make sure you get the location where you can download it. I've got a couple of questions for the panel, and similar questions comes from Kendall Christensen and from Dave Tonges on the biogenic fraction of the waste stream that you're handling, both Covanta and elsewhere. If there is a significant growth in organic treatment for that fraction, if we're going to divert more biogenic material out of the waste stream and into anaerobic digestion or other technologies, is there going to be an impact on operations at our current waste energy facilities? And if so, how big? Anybody?
Derek, you can, if you want to start, I can add to it also, but either way.
Yeah, sure. So, so diversion of organics is great. If that's practical, makes sense. We certainly are not opposed to it. And in fact, we are exploring the opportunity to have that technology co-locate. So that might surprise some people, but the Europeans have moved that way. We think that there's a definite synergy between a traditional mass burn plant and AD. It has a lot of benefits. So does it impact the waste in the MSW in the EFW plant? Absolutely, right? So you're going to change the heating value of the waste. The heating value is going to increase. We've got a couple responses for that. One is there's a lot of waste out there. In the U.S. in particular, we're landfilling over 250 million tons of waste a year. So the loss of a specific organic stream into a plant, be it residential or commercial collection of organics, it can be replaced. And then also there are organic streams that we think are likely to come into the energy from waste plant longer term. I mean, we have one project in Hawaii where we're co-firing biosolids because there's no market for the biosolids that come out, and there's as Bruce alluded to, there are issues with biosolids and land application. We think that could be a growing problem, and one that our facilities are actually set up to manage. So, it has the movement of organics will definitely have an impact, but I also think that there are other alternatives that allow us to manage heating value of waste to the point also where we have several of our projects today that we are injecting wastewater liquids into our plants. People might not know that, but it's been something we've been working on for the last decade as well, and has shown great results. So.
And Bruce, before you jump in, Bruce,
go ahead, Mike.
Add a little bit on Derek. We have sort of a unique capability. Since roughly 10 years now, we've been collecting stack samples of biogenic carbon for our greenhouse gas reporting requirement. And it's been remarkably consistent over the past 10 years, sort of like looking at a national average. And I just pulled up Long Island's, and looking at Long Island's data over the past 10 years, again, has been pretty consistent. Now, with that said, we do have a few facilities that have very aggressive organics diversion programs. The Durham, York facility that you saw that Bruce presented, our facility out in Oregon that we operate in Marion County, both of those communities have very aggressive organics diversion. Marion County even has curbside grease collection, to give you an example how aggressive they've been. And it has an impact on the biogenic carbon, but not as significant as you might think. Those facilities are running about 55% biogenic carbon versus the 64 or 65% we see on the island. So sorry, Bruce, just wanted to insert that.
Oh, no, not at all. I mean, I can speak to the operational aspects of it a little bit. And that I know it's more so we've seen the impacts in places like Canada that have, much mature sort of source separated organics programs like, Derek and Mike's facility out in Burnaby has been doing it for 10 years. And we have seen because of they're pulling out maybe about 60% of the organics from the waste stream, you see about a 3 to 3.5% on the order of that increase in the heating value of that waste, which, you know, can have an operational impact in that the temperatures in the furnace now are a little higher. But, you know, with refractory tile, I think, or Inconel, I think application in those boilers, I think Covanta has been able to stay ahead of it. But you do actually see a little bit of an impact on, you know, the heating value going up, which, you know, can impact throughputs because if the waste is hotter, you can't push as much through. So it does have a bit of an impact, and the increase in plastics obviously has a similar impact.
Okay, I guess I just had one question on the same topic, so to speak. Mike Van Brunt mentioned that you guys have been collecting data for a number of years now on greenhouse gas reporting. Could you just describe what you're required to report and how much data that the industry as a whole is gathered? I'm just curious as to how reliable the information is.
Yeah, we report, each of our facilities annually has to report fossil CO2 emissions, biogenic CO2. We also have to report methane and nitrous oxide. We're really pretty confident with the CO2 numbers. The methane and nitrous oxide numbers, we use sort of a default emission factor that, you know, when we actually have done some testing, it appears to be kind of way off, but it's a relatively small piece of the reporting puzzle. The biogenic testing data has been really interesting. So what we actually do, all of our facilities every quarter collect typically a 24-hour weighted sample from the stack and send it to a lab down in Florida, and they do radiocarbon dating on the actual stack sample. And so they can tell us pretty precisely what the split is between biogenic carbon and fossil carbon. And we do that quarterly. We have that data for each of our facilities over the last 10 years or so. And one of the things that, you know, has been a nice check against, you know, waste composition audits in terms of, you know, is the waste composition that we predict from a waste sort audit really playing out in practice at the facility? So it can be kind of another data point that you can use to figure out, well, how is the waste changing over time, if at all?
Okay, thank you. A question from Kendall Christensen about to Bruce, if you could comment on the state of waste energy projects in Canada, particularly GTA and Metro Vancouver, if you know anything about those.
Yeah, a little bit, and I play a Canadian on TV. My wife's Canadian, but Derek's the real Canadian. But I'll answer this question, and I'll let Derek chime in too. But you know, Metro Vancouver's been looking for a while. I think there's still a lot of political challenges there. I think they're interested in doing something, but there's nothing really. I think they had their hands slapped, for lack of a better term, when they tried to do it in the 2013-14 timeframe. They're still looking at options with their existing facility in Burnaby for either expansion or building something new there. But it's, you know, it's on the drafting board right now. GTA, surprisingly, Toronto is, you know, we were looking at a mixed, along with RRT, we're looking at a mixed waste processing project for Toronto, and they kind of pivoted with their current provincial government back to even considering waste energy, which was a 4-letter word in Toronto. But I'm not sure how far that's going. And the GTA right now, it's tough. It seems like there's a lot of focus in the GTA on organics and AD right now, and not necessarily thermal treatment of waste to energy. But there is a lot of interest on waste to energy from organics through AD, including in Durham, like Derek mentioned. Surprisingly, southern Alberta is in the province of Alberta, which, you know, where the oil sands sit, is very interested in moving something ahead. And they have some, you know, preliminary support from the provincial government. And surprisingly, we did a site study for them where we had communities almost not fighting each other, but competing with each other to actually house the facility. which was refreshing. So it's certainly not dead up there, even with, you know, a liberal government, but, you know, it's still, a lot of it is still on the, I think, on the drafting board, some of the, and they are more open to sort of alternative technologies, but those are really the projects I'm aware of right now.
I've got a practical question from Chris Andre at Brookhaven, and probably in somebody else's mind too, including mine. Do you guys, are you guys in a position to make any kind of a decent estimate of the capital cost of a new traditional grade waste energy facility with the latest and best emission technologies, what that might run on a, you know, dollar per ton basis, or a, you know, just any kind of metric that you can come up with? Maybe, you know, Durham, York is an example.
We actually have two pretty decent examples. So if everybody's got a pen and a piece of paper, I can give you kind of a number. So Durham, York, which is about 160,000 tons a year, was a little over 200 million.
Okay.
250 to be precise. Sorry, Derek.
Yeah. Well, you're in Canadian. I'm
oh, that's right. That's right. I think, yeah, we got our dollar system mixed up.
Yeah. So good point for the Canadians on the call, but I'm going to correct you a little bit. I think it's more like 220. So I rounded. So we can use 220 there. And then Palm Beach, which Covanta, you know, bought the service agreement for, which is 1 million ton a year, which was built at basically the same time that we were building the Durham York project. So it's 1 million ton a year. Big plant was, you know, fully wrapped. I think it was $780 million, but I'm going to tell you, it had a lot of extra bells and whistles, including a very glorious visitor center. So, and both these projects actually had, you know, really nice visitor center build outs on them. Palm Beach is particularly spectacular, multi-storage, multi-level visitor center buildings as part of the plant. So that kind of gives you the ballpark between small and big. I think those are reasonably accurate, you know, today.
Okay.
Yeah.
Obviously, you get efficiency with size. So the costs come down with size on an installed per ton basis.
Yeah. I just, to add, Mike, I think Derek nailed it, but like 1,000 ton per day facility, I think it varies on location and what sort of emission limits you get stuck with. But we typically say on a dollar per process ton per day, like 350,000 or 400,000. It could be less, like Derek said, if it's a larger scale.
Okay. Question from Will Flower. Derek, I think, mentioned that you guys were injecting liquid waste into some facility waste streams, and he was asking if that's done at all on Long Island, and what the potential is for that.
Not done on Long Island. Our Niagara plant does a sizable quantity of liquids in New York State. So that would be the one New York State project that we're doing it at. And by sizable, it's almost, I think, 100,000 tons a year of liquids. And we have a plant in Indianapolis and Indiana that does pretty close to that as well. We have a couple of smaller plants that we're doing. And these are plants where we're actually injecting these wastewaters, non-haz wastewaters, directly into the boiler units as a form of treatment. So the customers might be manufacturers, might be pharmaceuticals, where they're particularly concerned about where these liquids would go and whether there would be any residual fingerprint around these non-haz wastewaters. So we have a number of plants that are using reclaimed water from wastewater treatment plants, but we're using those waters as part of overall process water into the projects. So two slightly different things, but we viewed both those, and we've got significant experience around them as both being real opportunities for energy from waste on a go-forward basis for the industry. We think that capability is probably underutilized.
I got a question for both of you guys. You talked about York having, the latest and best air pollution control system that to meet both Canadian, US, and European standards. What's the physical difference between the newest type of APC systems and those that we have working on the Long Island plants now? And if something better is out there, how much better would we see emissions if put in place on Long Island?
You want me to take a crack at this one, Derek?
Sure.
Yeah. You're the technical guy.
That's frightening. I don't think, as far as like footprint or square footage, it's that much different. Particularly the acid gas control component of it, it's actually it's a dry system versus what most of the facilities, I think, or all of the facilities out in the island now would be the spray dry absorbers, semi-dry. So it's not a huge difference as far as I would say footprint. There's been some advances in sort of modularity that makes it, I think, a little less expensive to construct. And as far as emissions, these dry recirculation systems that Covanta implemented in Durham and that are being looked at in some of these other facilities, you get really good acid gas control, almost no emissions of SO2 or HCl, very low carbon monoxide emissions with the combustion controls in the furnace. NOx is about the same, but it could be ratcheted down depending on whether the regulatory body wants to force you or not. But, to Derek's point, it's not an SCR type system or that West Palm has, which can go very low. But it's and that does take up a little more space as well as costs. But it wouldn't. I don't think you'd. Certainly not a novice would look at that back end and see that it's significantly different, but it's certainly more efficient and removing a lot of those pollutants.
All right, folks, if you've got any other questions, give us send over a quick one or raise a hand. We are, I guess, about a half hour behind where we began. I'm happy we got everything in though. This was all very, very good and useful stuff. Very happy to have you guys. So without anything further, I guess we'll let everybody go home and go to lunch. But our best thanks to Michael, to Derek, and to Bruce for a very informative session. And we'll have another Waste on Wednesdays on the 28th. Featuring our own Caitlin Giglio, who will be talking about food waste in grocery stores and supermarkets and the contradictions that are bedeviling them. So I hope to see you in 2 weeks. And again, if you would like to get a copy of this, it's available. So let us know, and we'll give you a link so you can download it. And with that, I will say good afternoon to all, and thank you.
Thanks, everyone.
Thank you, everybody.
Thanks, everyone.